Exponential functions can also be used to model biological and physical quantities that grow exponentially. For example, population growth or radioactive decay are two examples that are modeled nicely by exponential functions. In general, we'll model exponential growth and decay like this. For growth, the amount or size of the population or quantity at time t will be given by a sub 0 times e to the kt. And for decay, the amount will be given by a sub 0 times e to the negative kt. In both of these, a is a function of t and represents the size or amount or quantity at time t. A sub 0 is the same thing as a evaluated at t equals 0, and it represents the initial amount or initial size of the population at time equals 0. K is the relative growth rate or decay rate, and t represents time. When k is written as a percentage, it represents the approximate growth in one time step. Let's use exponential growth and decay to model a population of E. coli in a petri dish. In an ideal environment, the population at time t can be modeled by the equation n of t equals 23 e to the 0.0347 t, where t is time in minutes. One thing that we'll note is that this uses n of t instead of a of t, and that's all right. We can use any letter to name our function. In this case, n would represent the number of E. coli cells at time t, so n of t is a nice choice for the name. To interpret the biological meaning of 23, we will first note 23's location. It is the coefficient in front of e, which is the same thing as our a sub 0. The first thing we might want to do is to decide if we should model this situation with exponential growth or exponential decay. And in fact, that has already been decided for us because we don't have a negative up here. Exponential decay is almost the same formula as growth, but there is a negative up in my exponent. Since I don't have that, I know it's exponential growth. That also makes biological sense because if I put some E. coli in a petri dish, I expect it to grow in an ideal environment. So we'll be using the growth formula. To interpret the biological meaning of 23, I will have to first look at where 23 is in regards to my formula. 23 is the coefficient in front of my e, which means that 23 is my a sub 0. That represents the initial size of my population. In other words, 23 E. coli cells are initially added to the petri dish. The number 0.0347 is the number that is my coefficient in front of my t inside of my exponent. That represents my k, the relative growth rate. This decimal corresponds to a percentage of 3.47%. This means that every minute, the E. coli population grows by about 3.74%. All right, so already we know that we started with 23 cells in my petri dish, and every minute my population is growing by about 3.74%. We can use this information to answer questions like, how many cells will there be in 60 minutes, and when will the petri dish have 1,000 cells in it? Both of these questions involve using our original formula, n of t equals a naught equals 23 e to the kt. Let's start with determining how many cells there will be in 60 minutes. In 60 minutes, I don't know how many cells there are. I don't know what n of t is, but I do know the time. In 60 minutes, the time will be 60. So let's plug the one thing that we do know into my formula. N of 60 is 23 e to the 0.0347 times 60. And we can go to the calculator to evaluate this. 23 e to the 0.0347 times 60 gives us 184.47. So there will be about 184 cells after 60 minutes. To determine the time when there are 1,000 cells in the petri dish, we have to decide what do we know and what do we not know. I don't know the time. That's what I'm looking for, so I can't plug in a time. But I do know that I want my population size to be 1,000. That is, I want n of t to be 1,000. So I can plug in 1,000 in for n of t in my formula and say 1,000 equals 23 e to the 0.0347 t. Now, what we have here is an exponential equation, right? This is an equation with a variable up in my exponent. And in earlier objectives, we learned how to solve these. We will start by isolating my exponential by dividing by 23, giving us about 43.478 equals e to the 0.0347t. And we can turn this into a logarithmic equation by either taking the ln of both sides or converting forms. In either case, we get that 0.347t is the ln of 43.478, and dividing by 0.0347 gives us the ln of 43.478 divided by 0.0347, the ln of 43.478 divided by 0.0347, or approximately 108.7 minutes. So it'll take about an hour and 48 minutes for there to be about 1,000 cells in the Petri dish. We can answer all sorts of questions now about the size of the E. coli population at various times, now that we know both the initial size of the population and the growth rate.